the volume of this color, this yellow region, divided by the total volume. So when I multiply them together, the total number of, say, the number of straddling modes is just lambda A d cubed k over 2 pi cubed. I'm just keeping the 2 pi cubed for some amusement. It doesn't, everything is only in order 1, and or vectors in order 1. Anyway. So basically it's just the same formula. It's just the volume of this region, this color region, times d cubed k. Now we want to integrate it. So remember the assumption, the working assumption is that each one of these modes contributes something on the order of 1 bit of entropy. So now we want, however, these are just modes of wavelength lambda. In fact, if I put this, if I use it lambda is 2 pi over, okay, so that, this aside. So the estimate for the entropy, just the number of straddling modes, is roughly equal to the integral over k from some minimum. I'm going to now assume that I do the integral between some smallest and some largest momentum of this dn, and that's equal to lambda a d cubed k over 2 pi cubed. So notice right away an A comes out. That's the area law already showing up. Then we have some vectors of 2 pi, and we get the integral of 4 pi d cubed k. So the lambda becomes 2 pi over k. K is now the magnitude of k. Everything will approximately isotropic in momentum space, and so we'll get this d cubed k is just 4 pi k squared dk. That's this term, and we still have the 2 pi cubed.
But couldn't you argue that this is already there in the assumption that the only modes to be counted are straddlers? So
it's already. All I'm trying to do is count the straddlers.
I'm saying that when you do, if you say that that's the only thing that's going to contribute to the entropy, counting only stragglers means that you focused only on this area times lambda part of the boundary.
Right.
So, in that sense, you've already picked out the area.
Oh, I mean, you mean one can see immediately why an area is coming in.
Right.
Yes, almost. Yes, that's true.
It seems, but I mean.
So I think the area law is very intuitive, actually.
But to say then that only so somehow now you have to say why only these stragglers contribute to the entropy.
If I wanted to turn this into a rigorous derivation, I would have to do that. So we'll see later when we do the more mathematically correct calculation, then one will see that.
I think that once you make the assumption that the state that they get summed over all the states n, and then you have a basis which is equally spread in momentum and then this is automatically solved, right?
Yeah, I think that's
so
right.
it's a summation over n is where all the area comes in.
Just to make it not sound more trivial than it actually is, when we finish this calculation, we'll see that in 1 plus 1 dimension we don't get an area. That's this famous logarithm that also has been derived in other ways. And then, but I agree, as long as we're not in 1 plus 1 dimension, this area law is sort of, it's the most intuitive and natural thing. I've sometimes been bemused because people who do this in dense matter seem to think an area law is some sort of miracle, or they used to think something very strange and rare, rare and wonderful. But in fact, it's the most common thing. From my point of view, the only thing that really needs to be explained is why you don't get an area law in certain cases. there's a case that I won't talk about at all here, but it turns out, here I'm doing a relativistic free field. But if you were to look at a gas of fermions at a finite density, then it turns out that you don't get an area law in 3+1 dimensions. You get the area is corrected by a logarithmic prefactor that depends on the depends on this L, this scale of the region. So it's not that you always get an area, but my point of view would be if we don't get it there, we better think about why didn't we get it? What's going on there? I think there's an answer, but I will not deal with. So I just want to get across that the area law is not sort of just, it's not a triviality, but I agree with you. If you think this way, it's what you would really expect. So we'll see what happens now. 1+1, 2+1, 3+1 dimension.
Can I ask?
Yeah.
I mean, implicit here is assumption that the fields can be localized in B and in
Yes.
A.
In what? In B and in A.
A.
Well, everywhere, localized everywhere, approximately.
Yeah, sure.
You mean
I mean,
A
but I
is
mean,
By A, you mean this other region?
outside.
what B and the complementary B.
Yeah, okay.
Sigma. Okay. But if I take space-time, I cannot localize fields unless they are space-like related to each other.
Well, it's true.
There's a problem
So
of
it's true that it's very interesting to redo this calculation in the space-time framework. I find that more satisfying, and that's in this recent work that I referred to. I think it's published. I think it's on the archive, so it's work with Yasaman. I actually won't go to the exact. I think it's me, or I'm not even sure if I'm on the paper. But it's me. It's Yasaman Yazdi and Mehdi Saravani. I'm pretty sure they posted the paper. And it goes through an analogous calculation using the space-time formula that I referred to.
But how do you get
Then you do really honest modes. You solve the field equation, and it's done. It's just done in 1+1, and you're in a causal diamond like this, or a causal integral, and you look at modes that a certain set of modes which are suggested by. I won't explain where they come from, but a certain set of complete mutually orthonormal modes for this region.
what is
And you-
entangling with?
In this case, it's entangling with its sort of causal complement.
Oh,
So
it's a causal complement.
yeah.
Okay, fine.
So if this were sigma, I mean, this is like the region V, then you can extend V to a Cauchy surface of the whole space-time, and what you're talking about is entanglement between this V and its complement. In fact, you can always do that, right? Once you set things up on a Cauchy surface like this, you can always promote V to its domain of dependence, which is some space-time
I understand.
domain. And then you're talking about the entanglement between this and if you like, the domain of dependence of the complement, which is some region like this. So from a space-time point of view, it's like an entanglement between this region and this region.
That's correct.
From a spatial point of view, it's an entanglement between this.
I understand.
Of course.
I mean, Unruh effect also, the way these people do, it is what this is a causal complement that is entangling.
It's
But what, in the case of the black hole, so the horizon is dividing it. It is no longer clear.
oh no, in the case of the black hole, it's the horizon.
Why is it interior, exterior causal complements each other?
So here's a Penrose diagram for a Schwarzschild black hole. So in that case, it's actually, this is our exterior region. So in that case, this is the analog of this. And then the complement is this over here.
Oh, not the ones
It's in the-
inside the horizon.
What?
Not the ones.
It's not actually this, right?
Ah.
But if we were
Okay,
interested,
then I have the then this is not exactly what.
if we were interested in this kind of, if you were interested in cutting the black hole here, then what would happen? Then we'd have you'd have a region like this. Sorry, cutting the horizon. So we're interested in computing the entropy on this Cauchy surface, this partial Cauchy surface, rather than this one that goes through the bifurcation point. And it'll be this, and the complement will be whatever, I don't know, whatever it will be. Something like this. So now it is inside the black hole.
Speaking?
Yeah, I messed up the drawing. So, if you're interested in the entropy later on, this is sort of fictitious. This is never there in realistic astrophysical black holes, but this part is here. So, if we look at a surface sigma like this,
So you are just writing a Cauchy surface and computing the domain dependence.
yeah. So this is only a partial Cauchy surface now, but it's a Cauchy surface to the future here. So its domain of dependence is this yellow region here.
Yes.
And then its complement is in the region that you normally think of as being inside the black hole, the region that's really present in astrophysical black holes, for example.
But in that case, the singularity in the middle is coming in.
The what?
Singularity in the middle.
There's no singularity.
The singularity is here.
They're not on the Cauchy.
So I could draw a thing that would hit the singularity like this, but I'm not doing that. But of course, most of the point of the area law and everything is that most of the entanglement is coming just in the neighborhood of the horizon anyway.
Rafael, so this is sort of an intuitive, counting method to calculate the entropy, but it's not clear at least to me that this should be the same as that. But you are saying it can be shown that it should be the same as the entangled.
Yes, so,
Yeah, so that's what he said he's going
so
to
the,
show us.
what I was hoping we should do was to actually set up the. So that work is not 100% finished. That's why I said there was an interesting mathematical problem. But you can carry it far enough that it's clear you'll get an area law, but to get the exact coefficient is not yet known. Yeah.
The expression for dn that you have written,
Sorry?
the expression for dn strad that you have written,
Expression for
dn,
yes.
will it hold for large lambda?
No.
Large what?
It won't be good for large lambda. So, and in fact, there's no interest to it won't make any sense when lambda becomes comparable to the diameter of this. But we'll see that in fact that'll make a negligible contribution to the integral, so we don't have to worry about it. The thing we do have to worry about is the very arbitrarily short wavelength mode. Okay, so let's just do it's almost there. So this is a over pi times the integral of k, if I did it right. Some little algebra here. And basically you get k dk. If I wrote everything right here, this should work out to a over pi times k dk. And again, it's from k min to k max. So that's equal to, so this is just k squared, a over pi. By the way, I should mention, almost everything I've said before can be found in the old paper, but this intuitive description is something that you won't find there, that I sort of convinced myself made sense when trying to prepare these lectures. So, why have I written k dk? I want k squared, k max squared, minus k min squared. And so it's equal to, that's equal to a over 2 pi. There's a 1/2 there, so it's 1/2 k max squared minus 1/2 k min squared. So it's a over 2 pi, and then there's k max, we've said is 2 pi, if we put a cutoff at wavelength L, then that's the cutoff of k at 2 pi over L, so it's 2 pi over L. And then little l. And we might as well put the cutoff on large wavelengths where this argument is not making any sense anyway, where lambda is comparable to the scale capital L. And so we get that just difference, but obviously 2 pi over, not 2 pi over big L is much, much smaller than 2 pi over little l. And I could set it to 0 without making any real change to the integral. So basically we just get a over. So the 2 pi's cancel out, so we get 2 pi a over little l squared as a good approximation to the number of straddling modes. And that's why this is under the assumption that L is much less. So big L, and there's other implicit assumptions here that this shouldn't be a very the extrinsic curvature of this boundary shouldn't be comparable to L and so on. So this kind of rough mode counting we did here is valid. So the only reason I kept the 2 pi here, just for fun, was because this is exactly the formula for the black hole entropy. If you take this L to be the rationalized Planck length. Yeah, I'm sure it has no deep meaning. Since it came out so nicely, I kept the 2 pi's. So that was in 3 plus 1 dimensions. Now what do we find in 2 plus 1 and 1? Okay, so is there any question? This is the heuristic argument. So it's basically just counting the modes, but you have to, with a little bit of care, what you can see is that if you look at this integral that we did, k dk, obviously most of the contribution comes for the very largest k's, as you can see here, because the lower limit doesn't make much difference to the value of the integral. So because most of the contribution is coming from the largest k's, most of them are little modes which are actually small in extent compared to the size of B, and so it's a kind of self-consistency of the calculation. So any questions on this? I'm going to just do the same thing for 2 plus 1 and 1 plus 1, and then go on to the more precise analysis. Yeah, we're almost finished. Yeah, I see.
It's 3:30, so how long do you think?
Well, I think what I might do, this I can finish in a second.
Okay.
And then what I might do is just set up the other calculation and just jump to the end and tell you what operator comes out and needs to be diagonalized. I was hoping to go through, it is instructive to go through some detail of the calculation because one sees the area law coming out in a way that's not vulnerable to these kind of implicit criticisms that people are making, like, well, I don't really believe that step you took around. So it's just pure mathematics, and one can see again that the area law will come out. But I think I'm going to skip that. I think I'll just set up the problem.
So here's a question: should we try to schedule one more lecture? Maybe even not for next week, but the week after, when people are back.
I prefer to try and at least have a,
I mean, I'm
if someone
worried
wants
that
to work.
I'm worried that you'll skip over things that that people might want to see in more detail.
All right, let me do it, and then at the end, if people want to see more detail on those things, we can see about setting up more detail, not a lecture on more detail, or something like that. So that if we do the same thing for, now I'm not going to keep the 2 pi's and so on. Oh, did I say? Yeah, I said what K-max and K-min are implicitly. Maybe I should write it explicitly. K-max we'll assume is approximately 2 pi over little l. That's the way in which the UV cutoff comes in. K-min, for the reasons we discussed, is approximately 2 pi over the diameter of the region. So that was part of the calculation.
What goes wrong in systems where there is a Fermi surface and you don't?
Let's see. That will lead to the discussion period. Okay. One of the motivations to doing this was to understand exactly what's going on. So there are some I was talking to the people at Perimeter, and they were telling me that the Fermi surface has this strange thing. How can that be? So we sort of talked it over, and in the end, I think came to a reasonable picture of how it takes place. If I went through the details of it, I'm not going to have time for now, then I could point out to you at which stage things start looking different for the Fermi surface. But in terms of this discussion that we just had so far, I don't think I can pinpoint exactly the place where, let me think about it. I don't have a good answer to that right now. Okay, so now what did we have? We did the 3 plus 1 dimensional case. That gave us an integral. If I didn't just erase it, which I did, it gave us an integral of k dk. Right? If we were to do this in 2 plus 1 dimensions, it's easy to see that it's just volume in momentum space goes down, so it'll just be an integral of dk. And then in 1 plus 1, it goes down again by a factor of k, and we end up with an integral of dk over k. This led us to k max squared, a behavior like k max squared, which is like 1 over L squared. So dimensionally, factors of 2 pi that are equal, and so dimensionally what had to be here is an area, and that's the area law in 3 plus 1 dimensions. In 2 plus 1 dimensions, again k max squared turns into just k max, and so that's just 1 over L, and then what dimensionally has to be there is another area, but what it really means now would be a circumference or a perimeter, length of the boundary. But now the interesting case is 1 plus 1 dimension, where we get, we get a log of k max, because this is a logarithmic near, the important thing is the integral is from L inverse, which is k max, L inverse here, is the upper limit. So we get a log of k max, or a log of little l. So again, dimensionally, what that has to be is log capital L over little l. And that's a well-known form that shows up in conformal field theories, of which this free field, massless free field, is a special case. So that's interesting. In 1 plus 1 dimension, you don't get an area law. Because what would you even mean by an area law? If you're in 1 plus 1 dimension, then this region B, so in 1 plus 1 dimension, this region B is just, here's our Cauchy surface, which is just a line now. The region B is just an interval. Or if you, depending on which region you look at, you could even extend it to a half space. But it just either has one boundary, which is just a point, or a 2-component boundary, which is just 2 points. So the area is really just just a number, either 1 or 2, depending on how you normalize it. It's something twice that, just some pure number. So you would expect, if the area law were to hold, you would expect that the entropy would just be independent of the size of the region. But in fact, it's not. It has this like, it's almost like that, This would be L over L to the 0 would be independent. L over L to the 0 is kind of, morally speaking, very similar to log of L over L. But in fact, it is a log. And so therefore, you don't have an area law.
So don't you get 2 of these logs with the minus sign? Because of the 2 ends?
No, you can't get a minus sign because the entropy is always positive. And the intuitive thing is there would be a certain amount of entanglement. I'm just from this intuitive argument, I can't get a minus sign because all I've done is count modes. So I'm just asking how many modes are straddling the boundary. So there's another portion to the boundary, twice as many modes straddling the boundary. That's not quite true because some of the modes might be big enough that they meet both boundaries, but then you're in the regime where the approximation doesn't make a lot of sense. So that's the main thing. So S diverges logarithmically. Now I want to consider one other case. Well, I could actually skip this because it was going to be used in the further deduction. But let me say it anyway, since it's of interest in itself. Now, I said we were always considering zero mass, but in the 1 plus 1 dimension, it's useful to consider non-zero mass, because when you do the 3 plus 1 massless problem in a half space, something like this, so this would be sort of z equals 0. So it's a very simple region, simplest possible region, just a half space. Then, because there's a translation invariance along this x and y directions, you can split the problem, the diagonalization problem, into subproblems which are parameterized by the transverse momentum or wave number. Each one of those is a 1 plus 1 dimensional problem, and it looks like a massive 1 plus 1 dimensional problem. So, where the mass depends on the transverse momentum. And so it's of interest to think about the same heuristic analysis for the massive case in 1 plus 1. So this is in 1 plus 1 dimension. Now you expect, in the massless case, you expect that a given mode introduces correlations from across the whole mode. But if there's a mass, then you expect correlations not to extend past the Compton wavelength. So now we expect that the largest wavelength we should look at would not be the whole diameter of the region, but just the Compton wavelength, which is 1 over m, which is, if you do star h bar and c, it's just the usual Compton wavelength h bar over mc. That would imply that k max would be of the order of m, not 1 over L. And so in this expression, you expect that the S is now scaling like log of lambda max over L, which is the same as log of 1 over ML. Right? Again, the dimensionless number ML. And that's, in many ways, you can strengthen that in many ways, and from various exact calculations, it's known to be asymptotically correct in order in fact, the exact coefficient is actually known too. And you can get that by a Rindler mode argument. Anyway, there's no time to say all that. But I'll just remark that it's true. You can get, it turns out that you know what the coefficient actually is, and it's 1/3 here if you're dealing with an integral, a two-sided integral. Sorry. I think it's known, but I'm not 100% sure of that actually. What's known is that here there's a 1/3, that's known. But I'm not sure the status of it with the mass. This intuitive argument leads you to say that you ought to get the same coefficient here as you get here, because it's just a different way of choosing. Do you know, Anita, whether, or is it known for the massive case? Because the massive case is strictly speaking going outside of the conformal field theory.
I don't know.
Yeah. So I'm not sure. So if it's not known, it would be nice to prove it. But that's certainly what the intuitive discussion leads you to expect. Okay, so now I want to set up the, it's going to be pretty mysterious, but I'll just tell you what the problem is that comes out. And I have a homework problem too, if anyone wants. But we won't solve the homework problem in lecture, but you want to think about it. So if you, let me state the homework. Well, let me do the other one first, and then I'll state the homework
I
problem.
think that that's when you're going to explain why these neorizers, these localizers contribute to the.
Yeah, I'm not going to explain it. So But
You're going to set up the calculator.
I'm going to set up a calculator. So I've been keeping this all the time, so finally we can refer back to it. So to set, let's see, where is it?